All right. How's everyone? I like the research question. Thank you. Did you guys go enjoy the lightning storm last night?
I didn't know that happened.
I thought I was going crazy at first because like the neighbors have this light that used to be on, it was really bright. And then the window just kept flashing. You think it's like a strobe light or something? Like, this is crazy. And it didn't occur to me that like a 100-degree day, they were gonna have a lightning storm.
Yeah.
So my immediate response is blame the neighbors. Okay, so we're gonna move into fat metabolism today. I'm gonna stretch this one out a little bit because how do I effectively burn fat is a question people care about, that a lot of people care about, maybe not everybody. But two of the major topics that we'll do are how do I gain muscle and how do I lose fat? What are the cellular mechanisms? What supplements? What techniques? What does science have to say about, in this case, shedding fat? And so for today, we'll just get through lipolysis. And then on Monday, I want to sort of finish beta oxidation, electron transport chain, really briefly, sort of quickly go through those things. I want to spend more time on lipolysis because you can interact with that. Lipolysis is a point of interaction. Beta oxidation is a little bit, electron transport chain, I don't know anything where you can interact with that in an effective way. So some prescription of a supplement, a diet technique or exercise technique where you can manipulate that. But lipolysis has a lot of points of manipulation. And at the end, hopefully on Monday, it might be on Wednesday, but at the end, we'll go through every supplement. There's a lot of supplements that have made bold claims for weight loss, and those bold claims are falsified whenever they run a falsifiable experiment. There are some supplements that make bold or at least, modest claims, and they're probably true. There are some maybes in the supplement category, and then there are some supplements people have never heard of that actually do work. They're not as popular as the ones that don't do anything, but they are effective. And then tricks in terms of how to do cardiovascular activity, tricks for thermal regulation, things like that. We'll talk about it. Maximizing fat rate, fat loss, the rate of that. But for now, we'll just start getting into metabolism. Updated scores after the points from whatever it was Wednesday. Team 3 is still winning, but there's some competition. Be thinking about your team names. I think over here was like Jaman. I have a song set in my head now. It's a good song. It's a good song. Yeah, so for the initials, we get a Bob Marley song. But whatever your team names are, maybe like by Monday after the weekend, come up with team names. Chat with your team and come up with a name. And the winner of the team name contest, the most creative or clever or funny or whatever one, I'll give points to. You know this one. Pretty soon, I'm going to export all of the case studies in a PDF, and I will upload that PDF with all the case studies. By the end of the weekend, I'll get it uploaded because there's some more case studies in this lecture, and we'll keep going through case studies. And as we go through the class, stuff like how do you lose fat becomes a case study too. Yeah, you want to do a little risk assessment, but then you want to also be able to prescribe nutrition and sleep and exercise and supplements and neat non-exercise activity thermogenesis. All of these little tricks to maximize fat loss, that's a case study too, and we'll start putting those in. So you know that one, you know the Freddy Krueger one. The Gandalf and Dumbledore one, you have that. I'm just going to read a few. We're not going to answer these today. I'm just going to read them so you know the types of case studies that you might be held accountable for, especially in like a team versus team competition. So far we've talked about cardiovascular disease, right? We've talked about diabetes. We've talked about cancer. We've talked about kids. So case studies on those topics are now fair game. So Gregory House, MD, was born in 1959 and reared by John and Blythe House. He traveled for much of his formative years, spending the most time in Egypt, Japan, and the Philippines. His mother is alive and healthy for her age. The identity of his biological father is unknown. House completed his undergrad at Johns Hopkins and was admitted to medical school there, but was expelled for cheating. He completed medical school at the University of Michigan. Shortly after, during a game of golf, he suffered a skeletal muscle infarction in his right leg. And so what we're looking at is an embolism, an embolus, right? We throw this thing around, this clot, cardiovascular disease, a clot forms. And so that we have something to work with. If you've had me a long time ago, it's been years since I last talked about this. It's been years. It's been like, the last time I talked about this was probably like your 129 class. But oatmeal is up there for a reason. And a couple of you are going to remember that. We can talk about it later. The necrotic muscle was amputated, and he still experiences pain today in the year 2012. So when you're calculating his age, it is currently the year 2012. The last year in which he serves as head of diagnostic medicine at Princeton Playsboro Hospital in New Jersey. Drug addict, enigma solver, and bitter curmudgeon, House fancies himself the medical equivalent of Sherlock Holmes. His unorthodox methods have created an anxious social environment, which includes romantic tension and strain between colleagues. He's 6'2", 180 pounds, single, blue eyes, brown hair, total cholesterol of 197, HDLs of 51, LDLs of 134, systolic pressure between 120 and 135, depending on the day. Remember, he's stressed, he has disrupted sleep schedule, something like that. Diastolic blood pressure of 75 to 85, fasted glucose of 110 to 130, limps about 6,000 steps each day around the hospital corridors, has an inconsistent sleep schedule, and one quasi-friend. So what you would want to do with that one is figure out the risk stratification, one of those 6 camps in which he can live based on diagnoses, history of diagnoses, based on signs, based on symptoms, and then go through and figure out within that camp, how many risk factors do we have? When you're stratified there, how many risk factors? So that's heart disease when we start thinking about that one. Okay, so now that was the 2012 one. Now we rewind the world a couple of years. It is currently 2010. And everything on this is true, except I think he's 5'8". I have no idea what his weight is. He definitely was a heavy smoker and a heavier drinker, and I just made all this up. So it is currently June 2010. Last month, May 2010, Christopher Hitchens published Hitch 22. In the opening pages, he wrote, when I first formed Hitch 22 is his memoir. When I first formed the idea of writing some memoirs, I had the customary reservations about the whole conception being perhaps, quote, too soon. Nothing dissolves this fusion of false modesty and natural reticence more swiftly than the blunt realization that the project could become, at any moment, ruled out of the question as having been undertaken too late. So he published that in May 2010. June 2010, early June 2010, he goes on the Jon Stewart Show.
My guest tonight, contributing editor to Vanity Fair, best-selling author. His new book is called Hitch 22, a memoir. Please welcome back to the program, Christopher Hitchens. How are you, sir? It's a bit early to say. Stop. 6 p.m., my friend.
So he had just been diagnosed with cancer right before this show. He published this thing in May 2010, talking about, this is probably too early. I'm a little bit too young to do a memoir, but if it turns out to be too late. 1 month later, he's diagnosed with cancer. And he didn't tell Jon Stewart the reason it's too early to say. It's like, it's 6 p.m. He didn't say, well, I was just diagnosed with cancer like an hour ago. His father died from that same cancer in 1987, accepting his mother's suicide in 1973. The rest of his relatives are healthy. Before Francis Collins takes over his case, we'll talk about him later, head of the Human Genome Project. Before Francis Collins takes over his case, he comes to you for instruction. He has no notable signs or symptoms or other diagnoses. He's 5'8", 185 pounds, very heavy smoker, very, very heavy drinker, 205 total cholesterol, 128 LDL, 52 HDL, 212 on triglycerides, HbA1c of 5.7%. His BP is 128/84. He rarely rides bicycles in Central Park. That part is true. Has slight PTSD from voluntary waterboarding. That part is also true. And he plans to continue on the lecture and debate circuit. So he wants to continue to be active. What would you do with with a cancer patient, someone with cancer who wants to continue to be active and has this history and hasn't been physically active in the past. So that would be a cancer case. Now this was just a little bit silly, but coming up with the idea of diabetes, what would you do with a client or a patient with diabetes? It is the year 2 ADY. I don't know what that means, but I think he died in year 4. His Excellency, Java, blah, 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 Hutta, Eminence of Tatooine, the Hutt gangster, comes to you seeking your counsel on diet and exercise. Mr. Hutt has decided to train for the Tatooine 2 Moon Marathon, T squared, M squared, in approximately 12 months. To prepare, he must lose at least 20% of his body mass and improve his VO2 max. So losing 20% of his body mass, that's the stuff we're starting to talk about today. We've already talked about diabetes and obesity, a little bit about obesity. We'll comment on it a little bit more today, but how do you effectively lose body fat? We'll be talking about that stuff today. He's a renowned goods trafficker who conducts all trafficking from a seated posture, so he's sedentary. He is unwilling to take time off work to prepare. There's probably a lot of stress. Mr. Hutt reports intermittent claudication in his distal tail during prolonged locomotion. According to the Galactic Republic of Sports Medicine criteria, Hutt has type 3 diabetes, diabetes. It is similar to type 2, except the insulin receptors aren't merely insensitive, they're fully immune. So it's just extreme type 2 diabetes. So you just treat this one like here's somebody with very extreme type 2 diabetes. Those receptors have no interest in bathing.
That is that important, but ABY is just
Okay, perfect. So ADY is a unit of time. He was born, when does it say he was born? Have I not gotten there yet? Born 600 BBY. Look at that. I don't know my Star Wars history or whatever. Are you team 2? Team 2. 0.03.
Kids are watching Star Wars.
Have you not watched
Yeah, that was the thing. That's just the ABY.
ADY, yeah, I don't know. I know who that is. So whatever, he has type 3 diabetes. Really terrible type 2 diabetes. He's the first identified creature to exhibit it. He has no other signs, symptoms, or diagnoses. Mama and Papa, which are apparently their names, I looked it up, Hutt exhibited similar obesity and perished from natural causes before the Clone Wars. No other details provided unless JP knows those details. I was unable to locate them.
I think it's just, I think the Hutts are just like a mafia family. I'm pretty sure it was just wiped out by another family.
Okay.
When the dust settled,
Okay.
and there's no one empire.
0.03, 0.39. His erect height, I don't know, 3.9 meters. His weight, over 1,300 kilograms. Born 600 before the whatever. Battle of Yamata. Okay, that. His blood pressure is 136/94. Fasted blood glucose of 445. Yeah, type 3 diabetes. 445 seemed reasonable for type 3. LDL 160, HDL 62, triglycerides 325, and he smokes. I think that's what this is. He always, in like every scene, he has some sort of like hookah or something there with him. So, but the idea, this one's silly, it's a little more playful, but you're going to have tons of patients coming to you, tons of clients, maybe family members who have diabetes, and you have to know how to do it in a less silly version. Last one, does anybody know who that is? 0.053. Team 2 is, JP is on a roll. On behalf of Team 2, JP is on a roll. Nemo is a little boy, I guess it says right here, but you knew it right. Nemo is a little boy with a pet squirrel named Icarus. Whether he's awake or asleep, he has a vivid imagination and cannot resist the temptation of his own curiosity. So he routinely finds himself in dangerous predicaments, and he always has the same excuse. It wasn't me, it was Flip. Flip made me do it. Flip is a stout and stumpy clown, he's this green clown, whose mouth is never without a cigar, and whose presence is never very far. Let's throw in a little rhyme. Nemo has recently met Princess Camille, who doesn't care much for boys who spend their lives in pajamas. I'm more into the athletic type, That was her response to Nemo's boyish advances. So Nemo has decided to become an athletic type. Morpheus, a father-like figure to Nemo, hires you to design an exercise program to make his son figure a more strapping lab. What advice would you give? So we've gone through that in terms of you're working with kids, children, adolescents, before they're mature enough, before enough maturation has happened where everybody sort of exercises and there are no weird claims about it. What would you say to somebody who really doesn't have any problems? He just has goals and he's little. So that would be another type of case study you might be held accountable for. You remember the history stuff. Now remember, in doing case studies, as we move forward, these case studies are going to be about topics. They're going to be about fat loss. They're going to be about muscle gain. They're going to be about maybe athleticism or something like that. They're going to be about achievements, accomplishment of some particular goal, using science, using physiology to become a better whatever. That's what they're going to be about. But step one, the first thing you always do is you go through these signs and symptoms or diagnoses and stratify accordingly into one of these 6 groups. Do that even if the person's 10 years old. Now, if you're asking a high schooler, really you can just say, or a college student or a 20-something out of college, right? You say, are there any diagnoses in your life? Are there any symptoms you experience? Maybe it's breathing, maybe it's something in your heart, maybe it's some pain you experience. Is there anything at rest? Is there anything during exertion that you've experienced in the last few years? And if they say no, you just sort of assume, like, all right, there's probably nothing going on here. Are you sure? You don't need to pry and pry. But especially with people, you get above the age of 50 or so, and it's worth expanding on that question a little bit and saying, how often do you go to the doctor? When was the last time you were there? When was your last physical? What are we talking for? Are there any diagnoses we're working with? And then move on to, are you experiencing any symptoms? Or is there anything you've noticed? Glance at the person's ankles, be a little bit more thorough. It doesn't need, unless they say yes, or give you some indication that the answer might be yes without saying it, you don't need to spend more than a minute doing this. If all indications are the answer is no. And then it's helpful to do the next step. Remember, the first thing, put them in one of these 6 categories. The next thing is within those 6 categories, what are the number of risk factors? And just have that written down somewhere. Whenever you're doing case studies for this class, if you're held accountable in a team versus team or on a test as an individual, you can have notes. You can have all this stuff written down. That's totally fine. You can show up with this table. You can have all of that, because in real life you can too, right? You can just have a little folder or one of those, you really don't have one in here. Those little clipboard things that everyone used to have. If you have a gym whistle around your neck and a little piece of wood with a little clip on top, you guys know what I'm talking about. I'm explaining really badly. Yeah. People have written information. That's fine. You can show up with that stuff. The importance of blood pressure. Coronary artery disease, what that looks like, the importance of vasodilation, what exercise can do to it, the interaction with cholesterol, the HDL, LDL relationship, the response or the interaction with the immune system, right? If you have a high white count, that puts you at an elevated risk. As you start going through this, when you're getting all this oxidative stress and the macrophages showing up and the chemotactic signaling, if you have an elevated immune response, you're looking at an increased risk there. And then we're going to get the atherosclerotic plaque developed here. And then the crack in the plaque, right? So it can harden, and if it cracks, bleeds, it has to clot. And once that happens, that embolus is a clot breaks free. If you're Gregory House playing a game of golf and that clot breaks free and it lands in the skeletal muscle of his right thigh, right? That's a skeletal muscle infarction. A heart attack, acute myocardial infarction. It could be a stroke, it could be a pulmonary embolism. An embolism just lands somewhere, and downstream from that, you're going to have a problem with whatever tissue is there. Nerves, like the central nervous system especially, is really, ischemia is not something nerves handle well. Some tissues handle it better than other. nerves are not among those tissues. And so, exercise does a lot, but there's an upper limit of what exercise is going to do. As you start prescribing things, there may be an overtraining case that you'll describe of somebody who's just way too much road work, or they're doing daily doubles in their sport, and it's just too much. You're like, look, your heart doesn't even look good anymore. Like, let alone you're exhausted and you have adrenal insufficiency and you're getting sick all the time from elevated cortisol and then all of these problems, your performance sucks. But your heart sucks too, because you're trying too hard. The good news is try less, sleep more, give up a little in life, and you'll be healthier. So there is a too much, and there are also responders and non-responders. And a healthy responder to exercise is going to be like your HDLs go way up, your systolic blood pressure goes way down, depending on what your blood pressure is. You don't want to get too low. You don't want to be hypotensive. Your insulin goes way down. These are responders, as opposed to like, I exercised a bunch and nothing happened. I exercised a bunch and nothing happened, and nothing happened, and nothing happened. You want to be on the good side, but there are adverse responders too, and being aware of that. In the case study, you can say, it's been a month, it's been 2 months, it's been a while. Let's retest you and see if you're responding favorably. And if you're not, we're going to tinker with some stuff. Now, this is what we're going to talk more about today. 40% or so, something like that, of adults and obesity. The risk of diabetes goes way up with obesity. One explanation is an excess of sugar, and we'll talk more and more about that and what sugar's role is. But one strong explanation is just like you eat a bunch of sugar and your body really can't process that very well, because you only have like 4 grams in your bloodstream. And you have a pound of glycogen on board, more or less, depending on body size. Nathaniel and Marie have very different amounts of glycogen, different body sizes. But in general, you might have a pound of glycogen, ballpark figure, and about 4.5 grams of glucose. So when you eat sugar, that goes up. You remember what insulin does, binds to an insulin receptor, a little protein in the membrane of a cell. So this is out of the cell, this is in the cell. A signaling cascade happens, and we're going to mobilize GLUT4 to bring sugar into the cell. We become immune to that, and that's what type 2 diabetes is. Remember, type 1 diabetes is those beta cells in the pancreas just sort of give up in life. Type 2 diabetes, 95% of all cases of diabetes mellitus, is these insulin receptors grow immune to the big doses of insulin that just keep knocking on the door all the time. You just get sick of it. And the other thing, remember, they're turning on glycogen synthase, going on with glycogen synthase. So carbs come into the cell and they get stored as glycogen, as opposed to being consumed. Insulin is a storage hormone. Insulin is a hormone. We'll talk about it with protein later. We'll talk about it with fat a little bit today, how it turns on fat storage as well, but it also turns on protein storage. Insulin is going to turn on storage. It's very anabolic, growth-oriented. PKB, protein kinase B, is what insulin is doing its signaling through. This is sometimes written as AKT. PKB or AKT, protein kinase B, super anabolic. And with protein, with fat, it just depends on what cell you're in. And insulin is anabolic all over the place. So you want to be able to talk about diabetes. You want to be able to talk about metabolic syndrome. There may be case studies on those. There may be patients or clients on a test that have those things. So you know the risks for metabolic syndrome. You know it's a constellation, it's a presentation that's multifaceted. And you just need 3 facets of these things to be classified as having metabolic syndrome. And metabolic syndrome puts you at risk for just so much more. You do not, once you have that, things just start to go sour, right? It's like if your fridge, it's like turning your fridge up to like 52 degrees or something. Like everything just gets rotten in there. That's like metabolic syndrome. It's like turning your biological fridge up so everything just gets rotten. That's a bad analogy, but you get the idea. Once you have metabolic syndrome, everything starts to go awry pretty quickly. Okay, insulin, what's insulin? Storage hormone. What releases it? Pancreas. What cells? Beta cells. Under what conditions? Yeah, a bunch of carbs in the bloodstream. Now, certain amino acids, you're going to get an insulin response too, but the real trigger, the big bold trigger, is going to be blood glucose. What does it act on? Cells. Yeah, we can ignore this stuff down here, but what effect does insulin have? Anabolism, GLUT4 translocation. It's going to be mTOR. It's going to trigger mTOR. We'll talk about that later for muscle protein synthesis. It will act on fat. It will act on carbs. It acts on a lot of things. Glucagon, which one does that come from? Alpha cells. And this is releasing. This is the opposite of insulin. Glucagon comes from the alpha cells. I don't know, 20% or so of the cells. Much fewer alpha cells than beta. And that is going to have the opposite effect of insulin. You're going to be releasing carbs to try to manage your blood sugar, right? If your blood sugar gets low, especially if you're not keto adapted, if your blood sugar gets low, you get loopy. That is not a happy place, or maybe it's happy, but it's not an articulate place to be. So there's your pancreas. Everything your pancreas releases, remember, goes through the liver and then gets into systemic circulation. Insulin, there's a lot of drugs you can take, or for diabetes rather, there's a lot of drugs you can take, and they do take insulin, even type 2 diabetics. Ask an endocrinologist what they're prescribing for type 2 diabetes, and insulin's on the list. Why is insulin on the list? They don't, what else are we going to do? Like, their body is insensitive to insulin. You still need to get drunk, hypothetically, in sort of by way of analogy. And so why don't you just drink more alcohol? You know, if your alcohol tolerance is like through the roof, then just have another bottle. You'll still get drunk, right? And with insulin, you got to get those carbs out of the bloodstream. Like, you have diabetes, whatever. You have type 3 diabetes, your blood sugar is like 445 or whatever. What do we got? Just give me even more insulin. I don't know. We got to get those carbs out of the blood somehow. So commonly, insulin gets prescribed. Now, when somebody with type 2 diabetes or somebody who's pre-diabetic is taking insulin, what's the long-term consequence?
They become less sensitive.
Yeah, they're going to be even less sensitive to it. Right, it's even worse chronically. It just like really messes shit up when they do that. But it's better today, right? You're a little bit better today. It's the same thing as somebody who needs to get back on the court or back on the field or whatever, and so they're doing a bunch of NSAIDs. Like, okay, that's better today, right? But a year from now, that's worse, right? You are sort of surrendering any future capacity for your ability to perform today. So that's the same thing with if you're doing insulin. Remember Herodicus, just go exercise, right? And Metformin, the AMP deaminase inhibitor, we're going to activate AMPK. AMPK is much better for diabetes at managing blood sugar than is insulin. AMPK is. AMPK has tons of effects. But just remember the main ones over here: mobilize GLUT4, halt glycogen synthesis, glycogen synthase, and turn on glycolysis, hexokinase and PFK. And then when we start getting into cancer regulation, we're looking at AMPK having a ton of roles as well, especially prevention. AMPK is like our best natural cancer prevention molecule in the body. I mean, this is really good at preventing cancer. Once you have cancer, it depends. The context depends a little bit. Often it's still helpful, but there are conditions in which it can protect the cancer. So remember with kids, it just has to be properly designed. All that old lore about like lifting weights, you're gonna like bust up little kid bones and stuff, like that's not true. You're stunting growth, right? You're not doing anything particularly unsafe or harmful. The risk of injury in weightlifting is lower than it is in anything else they're doing at recess, as long as it's properly designed. You can't go crazy with it. But there's tons of misconceptions that people still talk about today. Tons of misconceptions. And the evidence is just now overwhelming. Meta-analysis after meta-analysis of this. Everything we were saying in gym class or the sort of old husbands and wives' tales. That's all crazy nonsense. And so lifting weights is totally fine. Athleticism, however you characterize it, long jumps and sprints and squat jumps and throw and vertical jump, all of these things, weightlifting, you're improving them. Muscle strength, muscle power, linear speed, agility, direction change stuff, throwing, sport-specific performance, weightlifting, you're improving them as a kid. Now, what are you supposed to do, right? What are the prescriptions? Well, as long as it goes on for a while, you're not going to improve anything with a week, right? You want to have a longer term training, 2 to 3 times a week. You want to train them somewhere in that range. Number of sets, 3. There's going to be diminishing returns after 3. Once somebody's very athletic, they're a little bit older, maturation has happened, they have a history of exercise. Now you start increasing all of that stuff. But all these old claims about like, well, kids don't have enough testosterone and every kid has a little, cartilaginous skeleton that's just going to like bend and break. It's like, none of that's true. Okay, so let's talk about fat metabolism. We'll start again just by chatting a little bit about BMI, body proportions, how we characterize fat, how we measure fat, and then we'll start to get into the cellular mechanisms of loss. And again, next week we'll talk about all the tricks. How do you do it effectively? So ectomorph, mesomorph, endomorph, those are the 3 general body types, the classifications. Just look around you in life, wherever you are, and you're going to see people with different shapes. People are all different shapes and sizes. True. And we kind of lump them into 3 categories. Whoops. And so, in real life, there's like the Jack Blacks of the world. You think of like an endomorph, right? And then like a mesomorph, ectomorph, Manute Bull. Who knows who Manute Bull used to be? Nobody knows Manute Bull. Manute Bull was sort of like, the legend, and I don't know how true it is, goes that I think like Mormon missionaries discovered him in Africa somewhere, and he went. I can't betray all the secrets of where he was going that I was working, but he had like PR people in this little pamphlet that said like he killed a lion. It was like sleeping, I think, at the time. He sneaked up on a spear. But he had to duck. Look up Manute Bull, B-O-L, and the guy's height was outrageous. He could just like dunk and like goaltend without jumping. So, but remarkably unathletic. But he's like a Hall of Famer for his height. Very much an ectomorph. Very much an ectomorph. Now, how do we measure this stuff? How do we measure actual body composition? Well, there's lots of ways. Right? We have a hydrostatic tank right in the back. In the back, we have Fit 3D, that camera, a couple doors down that way. We don't have DEXA. You can do MRI, you can do calipers, you can do bioelectrical impedance. I don't like this one. This one, you just go to get your Omron, go to Costco and get like a $30. They're like one of those scales that has like a little footprints in like steel that you stand on. It says like, you weigh whatever, here's your body composition. Not really. These are pretty inaccurate for body compositions. I don't really like those things, but this is okay as long as like this sort of, there's like a tide there, and the scale is going to be going crazy, and so this can be a little bit sensitive based on what the scale is doing. If the scale is bouncing all over the place, you sort of eyeball it. I don't know. This is super accurate. This one. This is good for skin. Right, for subcutaneous, it doesn't tell you systemic body fat. It doesn't tell you your whole body composition, but it tells you how much subcutaneous fat you have in your triceps. It'll tell you that pretty accurately, and you can measure people's triceps over and over, or thigh or abs. Measure all those sites. But we don't usually do that when we're characterizing people's obesity. Are they underweight? Are they normal weight? Are they overweight? Are they obese? What we're doing is just using BMI. And you don't write down the formula or anything, but less than 18 and a half or underweight, remember this is risky. This is like Tyrion Lannister was 0.4. So that's like seriously risky. And we're getting increasingly risky up here. You get into this zone, it's like 100-fold, nearly 100-fold risk of developing diabetes in that BMI. Right around that low end in here, low end of overweight, something like that. That's really where you want to be. But we make assumptions. We make assumptions that the fat percent in someone who's underweight, like, oh, it's under 20, normal, here's your body fat percent, overweight, here's your body fat percent. Well, maybe, I don't know, it depends on a lot of things, right? So just to say, here's what your BMI is, here's the corresponding body fat percent, that's less accurate than any of these, right? That's less accurate than this thing. And so we want to be cautious in the interpretation of a BMI. So we all know He-Man, which I think is having like a comeback of some sort. I think He-Man is like back on the air. First appearance 1983. Prince Adam of Eternia. He's 6'11", 320. That's apparently his digits, like the back of the baseball card digits. And he trained under the guidance of Man-at-Arms. Notable feat, he hoisted him through Castle Grayskull. But if you do it, 6'11", 320, his BMI is 32.7. He is clinically obese. Physicians are going to talk to him about weight loss programs, right? Where is he going to cut from? Right? I mean, I guess he could get rid of some of his gear and his like lion mane Speedo. You can get rid of that. But like, where is he supposed to cut from? So a high body fat percent and a high BMI, these are not the same thing. And when we start looking at what's called healthy obese or skinny fat, right? So people can have a low BMI. They can have a BMI of, I don't know, 20, 21, 22, but a body fat percent that's very high. So like about 12% of men had a BMI that was overweight, but had good body fat percent. Right? About 6% of men had a normal BMI, but more than 25% body fat. So we're looking at maybe like 18% of people, of males, 18% of males are not characterized by the BMI. Now, most people are, right? I mean, that you're looking at 4 out of every 5 guys is well characterized, well-ish characterized by the BMI, but there's a lot of misses. And we see with healthy obese for women, this is Shira. She does not look pretty. She's supposed to be 8 feet tall. She probably has like a really low BMI. She's 8 feet tall. But this is supposed to be the corollary to He-Man. Healthy obese, 3% of women had a lot of muscle mass. And so they had a BMI that was elevated, but relatively low body fat. And about 15% of women were, quote, skinny fat. Meaning, like their BMI is fine, they're not categorized in any risky class, and yet their body fat percent gets elevated. Now, when we start to put these two things together, we get a clearer picture of a risk. So the hazard ratio, 1 means like nothing. As we increase, we're looking at mortality risk. These sort of factors of increasing the risk of mortality as we go up. And this is a low waist circumference. And this is a high waist circumference at the same BMI. So this is just, we're at the same BMI here, we're at the same BMI, at the same BMI, but a lower waist circumference at the same BMI corresponds to, especially at this lower end, it sort of starts to come together a little bit toward the end as BMI gets like 35 to 50. But in this low end, right, what we're seeing is waist circumference matters a great deal. It's not just how heavy are you, it's waist circumference. And so the prevalence, remember we're talking 40%, something like that, somewhere around there of adults, the prevalence of obesity. And you can do state by state. If you go stateofchildhoodobesity.org, adult-obesity, you can look at adults. You can look at I think this is from 2019. So the latest data are from 2019. And the different states, Colorado is the only one that's sort of hanging on, doing okay. Okay, but you look year after year, here's 1990, here's 2019, adult obesity just keeps going up and up and up and up. The US, we always talk about the US, how bad it is, but here's the average. Now the average is dragged to the right by these outliers, but the US is none of those outliers. Oh man, it's hard to read, it's so tiny. Oh, the US is like somewhere around here, United States right there. That's us. Right there in the US. Australia is probably up here somewhere. Liam, I would try to read it, but it's just, here's the UK. That's about all I can read. There's others, Hong Kong. But so there are, I mean, like, you know, percent of, and this is from 2021. This is like, I got it this morning. Here's the address where it came from. You know, like 75% of people are obese. I mean, that's a lot there. But, you know, the US is not one of these top 10, but we are particularly bad. Outside of the US, now there are age and racial implications when people start dividing these things. And in the developing world, you know, I mean, this is from 2014, 1 billion obese people in the developing world, right? So it's not just places that have, you know, beyond luxuries, we're indulging in excesses. It's not just that. And when you start to analyze things like in childhood obesity, isn't just the US either. So the prevalence between 2011, 2012, their age greater than or equal to 20, whatever. And you look at Canada, and it's like, that's not remarkably different. You know, Canada and the US, not remarkably different. Is the US worse than Canada? A little bit, but not so much that it deserves any particular attention. And wherever the development is advancing most, I mean, if you just look at Beijing, 2006, it was 14%. By 2013, it was 20%. You know, right in that space, it's right there with the US, but that's just Beijing specifically. So worldwide, we're seeing obesity. The epidemic really is an epidemic. And we know the association with diabetes. Get that BMI up to 35, 40, and we're looking at this 100-fold increase in the risk of diabetes. But here's a 2021 article from the American Heart Association, and their statements about how obesity and heart failure are just, man, those things are tied. I mean, that's just, the heart does not want obesity. The heart wants you to thin out a little bit. Not necessarily BMI. No, it's not necessarily BMI. It's that waist circumference, right? As soon as you start to get abdominal adiposity, you start to get that visceral fat, that's when you start seeing this exaggerated risk of cardiovascular decline. So how do we remedy this, right? Well, it's metabolism. The crudest sentence that we could assign to this is calories in, calories out. That's not how it works, though. On a very fundamental level, that sentence is true, right? The number of calories you eat and the number of calories expended determines, you know, the difference in body weight. But on a practical level, that's not even close to true. Yes, it meets the criteria for truth, but it's not, that's not how it works. So we all know people who can go to like a baseball game and eat 25 hot dogs. It's like $20,000 for them. And they leave the game a pound lighter than when they entered. And then somebody else who's on a restricted diet eating 500 calories a day, and they're not losing weight. We all know these people, right? We also know people who started a drug, some medication. They were given a prescription for something, and their body weight was always normal. And they get on this medication, and like 6 months later, they're obese. Did they change their diet? No. Did they change their exercise? No. Well, what the hell happened? Metabolism happened. Calories in, calories out is not a practical sentence. That's not a prescription that you can give to somebody and think you're saying something useful. Because it's hormonal, right? There are genetics at play. There are also conditions that we can manipulate. And a lot of this is going to be hormonal. So when somebody's like, all I said is you have a slow metabolism, right? what the hell do you mean by slow? Because remember, metabolism is a summation of all chemical reactions in your body. Now, some of these are anabolic, some of them are growth, some of them are let's store, let's assemble, let's store, let's get bigger, and some of them are catabolic. Some of these chemical reactions are catabolic. And if catabolism is outpacing anabolism, you're losing weight. That's not calories in, calories out. Is catabolism outpacing anabolism. And that is determined by a lot of things. Is diet one of those things in terms of how many calories you're eating? Yes. Is the amount of exercise one of those things? Yes. Is that the bulk of the explanation? No. There's a lot more to it to explain in terms of the metabolism. And so the metabolic stuff gets really complicated. We're going to talk about the relevant parts. For now, the relevant parts are going to be mobilizing fat, getting it ready for consumption. Later, we're going to talk about anabolism, right? For now, we're going to talk about catabolism and how to optimize it. Next week will be optimization. Today, we're just introducing the idea of lipolysis, mobilizing fat, catabolic from the perspective of fat metabolism. Later this semester, it's anabolic, how do we grow? Getting into, just the basics, super basics. We all know ATP, right? There are 3 phosphates. Ribose, a little 5-carbon sugar. Who's eating ribose? There's someone back there that I left here. The little orange bottle, like right next to the coffee thing. Nobody ever wondered as a sweetener. You're not going to get like a blood sugar spike off of it. But so ATP, this is the currency, right? We've all had basic physiology. ATP, this is the energy currency of the body. ATP hydrolysis, we're going to lyse our ATP. We're going to chop off a phosphate. Here's that phosphate, right? ATP ACE, ATP ACE is the enzyme that does it. Water has to go in, hydrolysis, ATP hydrolysis. Water goes in because you chop off that phosphate, you chop that thing off, and an O and an H have to plug up that phosphate right here. That leaves one other H, H2O. The other H goes floating off. There's a pH change. And so when you're looking at, we're going to come back to this later, we'll talk about glycolysis, and everyone blames lactic acid for the burning, like exertional burning during exercise. Lactic acid, nonsense, like super nonsense. This pH, we're talking about acidity, that's pH, that's the H, that's literally the H of pH, and it's coming from ATP hydrolysis, it's not coming from glycolysis. But so this is how you release energy. Everything you're doing all the time, you're sitting here and you have a basal metabolism. You have a basal metabolic rate, your heart and lungs and liver and kidney and guts, your intestines, food absorption. Your brain is the biggest consumer. Thermal regulation, huge consumer, right? Keeping all of your ions where they belong against concentration gradients, huge consumer. All this stuff, huge consumers of ATP all the time. Skeletal muscle too. But we store very little ATP. I mean, seconds worth. Again, just because the ease of accessibility of like the smallest and largest body of 6'6" and something shorter than 6'6" in the river. And very different amounts of ATP on board. Very different amounts. I don't know, whatever. Who cares? But from this book, don't write this down. This is just a ballpark figure, but adenosine triphosphate. Basically, the human body turns over its weight in ATP daily. You don't store much ATP, you reconstitute it. You break it down, you break it down, you break it down. When you're exercising, Barbara Ainsworth puts out the compendium of physical activity. And we talked about that earlier this semester, where remember like that slide of somebody pushing somebody in a wheelchair, and the slide of like 51 axe blows a minute. There's like a lumberjack in there. You can get your metabolism up 20-fold, 25-fold, 30-fold if you're really exerting yourself. That's ATP consumption. That's you're really burning through ATP. And so you have to reassemble it. And I have to read this, like, Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. All the king's horses and all the king's men couldn't put Humpty together again. Nowhere does it say he's an egg. He's not an egg. That does not say he's an egg. You could not put Humpty Dumpty together again. Humpty Dumpty was an egg. Like, that's not how it ends. So maybe we melt this down to glue out of a horse and put it back together. In the body, right? In the body, what we're going to do is use our food, right? We store our energy outside of our body largely. We store some fat, JP Jeff.
I was going to say that somebody was telling me that but yeah, that's basically
Like that, yeah, a cannon, Humpty Dumpty. Yeah.
Fire horses.
I know, yeah. What do you do with like hooves? Do they have thumbs? How are they supposed to put anything together? Just watch a horse try to put together like a Lego set, and then we'll try Humpty Dumpty, a living creature that's maybe an egg. So we have fat, we have carbs, we have protein, and we can use this stuff. We'll talk about protein and metabolism for one lecture before we get into anabolism and protein. But here, catabolism, we're really going to focus on fat, but we're going to convert it back into ATP, right? So the ways of, the basic ways of doing this, and we'll talk so briefly, like one slide a piece for like creatine. You can take it as a supplement, but your body is naturally making it, store it in skeletal muscle, makes it in the liver. Creatine, adenylate kinase, glycolysis, like carbs, and oxidative stuff. But we'll just get through lipolysis today. And when we start getting into, so Krebs cycle, we're going to talk a little bit about on next week, because when we get into protein catabolism, Krebs cycle becomes a little bit important. But beta oxidation is a little bit important for fat metabolism. Lipolysis is super important for fat metabolism and how we interact, right? How we take advantage of this stuff. So creatine, adenylate kinase, carbs, right? Glycolysis, and then the oxidative stuff. And since we're talking about oxidative, this is where we're going to spend most of our time. Creatine, just all you need to know is the creatine kinase reaction. Creatine kinase is an enzyme, it's an ACE, right? So you have creatine phosphate or phosphocreatine, it just donates its phosphate. It donates its phosphate, you consume a hydrogen ion in the process, so it's acid buffering. But it doesn't last for very long. That doesn't last for very long either. I mean, if you're going to do a Wingate test, you know, your ATP, your free ATP, and your creatine phosphate are sort of checked out. You don't completely deplete at any time. You don't completely deplete because you're not going to die, but you deplete quite a bit. You deplete those quite a bit in a very short period of time. Here's adenylate kinase. Remember, you do ATP hydrolysis, chop off a phosphate, now you have ADP. Well, what do you do with the ADP? Well, phosphocreatine can donate its phosphate, or another ADP can just donate its phosphate. And so then you end up with two ADPs. One of the phosphates gets transferred to an ATP, so you wind up with an AMP and an ATP. And then obviously you have to dispose of the AMP. Cameron, what's our mechanism?
AMPK, AMP deaminase.
AMP deaminase, that is the mechanism. What team are you? I might could call on more people, but you're team 3. I'm gonna just give you very little.
Okay.
Like 009.
AMP, AMPK and mTOR and the cancer stuff. So you said cancer, AMPK is a great preventer of cancer. If we overturn on mTOR, could that cause cancer with our turnover?
Absolutely. Yeah. So, and we'll talk about this later. So AMPK is a massive inhibitor of mTOR, which is growth. You know, PKB, mTOR signaling. That's protein synthesis. That's how we're actually growing. And there's other mechanisms too, but man, this one's huge. So mTOR, this signaling cascade, that's really what's happening in the weight room. They're like, did you actually grow or did you just work out and nothing happened? mTOR. And certainly with cancer too. So people who have cancer or people who are at risk of cancer and they want to ward it off, minimizing mTOR signaling. There's just some funky stuff that you'll see in certain situations with AMPK. AMPK, think of it as anti-cancer.
Yeah,
It's anti-cancer.
they would just have a complete different exercise prescription for cancer patients.
For cancer patients, the exercise is critical, but fatigue. If you look up work there's a meta-analysis by Justin Brown. I think you met Justin a couple of years ago at UCSM. He did this 2 meta-analyses on cancer and exercise that were just enormously cited studies that talked about the response with cancer patients and exercise. And one of the things that they deal with is just fatigue that's unbearable. So it can be really difficult to exercise, but exercise remains incredibly important for them. And we can talk about that a little bit later as well, getting into, when we're more into AMPK and mTOR, and we can incorporate a little bit more cancer in there. So the adenylyl kinase reaction, we all know glycolysis. And later in the semester, we'll have one day where we talk about carbohydrate metabolism, and we'll talk about hexokinase, we'll talk about PFK, we'll talk about pyruvate kinase, and we'll talk about G3P dehydrogenase, glyceraldehyde 3-phosphate dehydrogenase. So we'll talk about those, and then lactate dehydrogenase, and sort of the different steps that are of consequence in glycolysis. But I'm going to leave hexokinase circled for just a second. When we talk about glycolysis, we're usually talking about yeast, right? This is we'll get into ethanol eventually, but hexokinase, this means you're starting with glucose. But how much glucose do you have?
4 to 6 grams.
Yeah, 4 to 5. Yeah, very, very little. You have very little glucose. And how much glycogen do you have? A lot. Let me tell you, you have a pound. No, 2,000. You have 2,000 of a ton. And hexokinase, that's what you use for glucose. If you're going to use glycogen phosphorylase and phosphoglucomutase. You get to here through a totally different pathway, and it matters. It matters that glycogen enters glycolysis differently from glucose, and we'll talk about that later. The carbohydrate metabolism, you get to pyruvate. What the hell do you do with your pyruvate? You don't just keep it, right? You're not a hoarder. You have to do. There's a endpoint for all of this stuff. It has to go somewhere. So you can convert to acetyl-CoA, or you can convert to lactate. Either one of these potential feeds of that pyruvate, of that end product of glycolysis. So that's a lactate dehydrogenase reaction. Notice you're consuming a hydrogen ion right there. So it's a buffer. It's a pH buffer. If you're going to do this, if you're going to make lactate, you're actually buffering acids. So who burns? What are you talking about? But everything else. Now we're getting into the mitochondria. Right? Let's get into the mitochondrion or the mitochondria. And the Krebs cycle, or TCA, tricarboxylic acid cycle, citric acid cycle, whatever you want to call it. You have oxaloacetate. Okay, this thing, 4-carbon acceptor compound. Okay, you have acetyl-CoA right over here, a 2-carbon compound that's going to come in and bind to oxaloacetate, make citrate. You have a 6-carbon compound. And then you just shed those 2 carbons. It's carbon dioxide and carbon dioxide. There's 1 carbon right there. There's 1 carbon right there. Right? Those are those 2 carbons. Right? And so when you bind it to oxaloacetate, that 4-carbon compound, to get this 6-carbon compound, you release one of the carbons, you release another carbon, and you wind up, after this cycle of enzymatic reactions, you wind up with oxaloacetate again, ready to accept another one. Later, I will probably talk about ketogenic dieting, ketones, right? Ketogenic, we're generating ketones. If you do gluconeogenesis, make carbs from non-carb sources, right? Gluco, neo, new, genesis, make. Let's make some new carbs out of stuff that isn't carbs. Great source, oxaloacetate. Let's take that and make some carbs out of it. Well, now the acetyl-CoA show up, and what the hell? My gate isn't here. I was stood up, and like 2 of them show up. So there's one, there's another, and they're like, I was stood up too, and so they go home together. That's a ketone, and so you're going to create ketones for the ketogenic dieting. We can talk about the details of how that works later. But we'll also talk about some of this stuff in protein catabolism, if we're not using it for the purposes intended. But just notice that in the Krebs cycle, you're getting NADH, you're getting FADH, another NADH. You're getting those in addition, that's GTP, guanine triphosphate. In addition to the carbon dioxide, you're getting NADH and FADH, and that's the stuff we'll talk about a little bit. Very briefly, we'll talk about those things next week. But fats, we can make acetyl-CoA out of fats as well. Beta oxidation, that's what we're doing. But before you get there, before beta oxidation, you have to do lipolysis, right? We're going to store fat in our, tufts and mounds and, our geography, right? We're going to store fat as triglycerides or triacyl glycerols. This right here is your glycerol, this little 3-carbon compound. Each one of these is a fatty acid. Right? Each one of these things is a fatty acid. And so a triacyl glycerol or a triglyceride, same thing, just different vernacular for the exact same thing, is glycerol and 3 fatty acids. What's a diacyl glycerol? 2. One of them's gone. What's a monoacyl glycerol? We got another one gone. We have 1 fatty acid attached. And so that'll come in when we're looking at mTOR, ways to turn on mTOR. A diacyl glycerol you can work with. And so there are some other things to do with these fatty acids other than lipolysis, let's burn fat. But where we are right now, glycerol, 3 fatty acids, we have to mobilize them, right? Lipolysis is that. We're going to go from here to there, right? Reesterification is you go from there to here. You can do that too. You can mobilize, like, you know what? I didn't put them to use. Let's just put them back together. It's fine, just throw them in storage again. And so sometimes in things like lipodystrophy, HIV patients, what you'll see is sort of a peripheral leanness and increasing abdominal adiposity. You'll see this in really stressful situations, high cortisol situations too. You'll get a lot of this, and then you'll get a lot of that. And where you're doing that and where you're doing that are in different places in the body. So what you want to do is lipolysis and then consume. You want to get rid of it. And there are a lot of good articles on lipolysis that characterize how it functions and what interacts with it. If you go to the website later today, when this lecture is up, you'll see all of these. So don't write them down. There will be a file folder that has all of those in there. But the neural innervation of white adipose tissue, we'll talk about on next week. We'll talk about white versus brown fat and some techniques of using brown fat for metabolism. But neural innervation, it used to just be thought that there's epinephrine doing everything. Epinephrine, right? It's released from the adrenal gland. It's a endocrine hormone and a mean hormone, a little tiny one. But norepinephrine, released from nerves, this is innervated, right? Fat is innervated. And so epinephrine and norepinephrine from the adrenal gland and from the nerves, both of those things are stimulating lipolysis. Non-adrenergic control of lipolysis. This is a really good article talking about some other mechanisms involved. Insulin's actions, how insulin is going to inhibit lipolysis, talked about there, but it looks like this. So epinephrine or norepinephrine binds to a beta adrenergic receptor. So epinephrine systemic, norepinephrine from the nerves, neurotransmitter. That binds to a beta adrenergic receptor, and we turn on adenylate, or you'll see it listed as adenylyl cyclase. That's the same thing, adenylate or adenylyl cyclase. What that does is it takes ATP, we all know what ATP is, converts it into cyclic AMP, little camps, 4 of these little guys. You take a group of these, attach them to PKA, protein kinase A. We've been talking about PKB, protein kinase B, and I say that PKB is arguably, I'm not saying it is, but it's arguably one of the most anabolic enzymes in the body, PKB. PKA is an extremely catabolic enzyme. Extremely catabolic PKA. PKB, extremely anabolic. But PKA, once it's activated by cyclic AMP, is going to phosphorylate stuff. It's a kinase. Kinases attach phosphates to things. A kinase is going to take phosphate and attach it to stuff. Either turn it on or turn it off. And so here you see hormone-sensitive lipase and triacylglycerol, diacylglycerol, monoacylglycerol. This is a triglyceride right here. Now, adipose triglyceride lipase is really the one doing this. So this does some of it. Okay, hormone-sensitive lipase, yeah, but this is really hormone-sensitive lipase is doing. Not as much. Adipose triglyceride lipase. That's really doing the first one. But, and then monoacylglycerol lipase. But hormone-sensitive lipase, PKA phosphorylates it, turns it on, and once hormone-sensitive lipase is on, this is a major regulator of lipolysis. It's hormone-sensitive lipase. So this is adenylate cyclase. We talked about adenylate kinase earlier as taking 2 ADPs and just swapping one of those phosphates. Adenylate cyclase and adenylate kinase, 2 totally different things. Adenylate cyclase, remember, takes ATP and converts it to cyclic AMP, which is this. Cyclic AMP, cyclic meaning this. Both connected. So if you want to see ATP or AMP versus cyclic AMP, there's AMP, there's the phosphate, right? Cyclic AMP, 2 points. Now, AMP does not activate PKA. You cannot bind AMP to it and say good enough. You can't do that. Has to be cyclic AMP that you bind to PKA. That's where insulin comes in. That's partly where insulin comes in. PDE, phosphodiesterase, PDE, converts cyclic AMP to regular AMP. So phosphodiesterase, PDE, converts cyclic AMP to regular AMP. So if this is on, if phosphodiesterase is on, you are not activating PKA. If PKA is not being activated, you're not doing lipolysis. When we look at insulin, we see this exact same thing. We were just at epinephrine and norepinephrine binds to a beta adrenergic receptor, turns on adenylate cyclase converts ATP into cyclic AMP. Insulin, anti-that, you see a little minus sign. Insulin, through PKB signaling, PI3K, PKB, through those, activates PDE, phosphodiesterase, which converts cyclic AMP into AMP, so this never happens. So insulin binds to its receptor is the single largest anti-lipolytic hormone you have. Insulin obstructs lipolysis. Step 1 in fat utilization. Step 1 is abolished. And if there's no step 1, there's no step 2. You need to go through step 1 to go through beta oxidation. So insulin is the single most obstructive hormone to lipolysis. And that's how it works through PDE. Here you see, beta adrenergic receptor. There's epinephrine. It could be norepi, but epi or norepi. There's adenylol cyclase. Remember, adenylate or adenylol cyclase, same thing. Converts ATP to cyclic AMP. But here's phosphodiesterase, converting the cyclic AMP to AMP. So everything's halted. There's nothing after that. There's no lipolysis after that step. Now here's adipose triglyceride lipase. Insulin has an effect on this as well. It's just not as direct, right? Insulin has an acute effect on lipolysis. Go eat a bunch of carbs and good luck trying to metabolize fat acutely, because insulin is going to block lipolysis and you need lipolysis. Chronically, there's an effect too. When we're looking at the expression, genetic expression of adipose triglyceride lipase. So insulin seems to have a chronic effect on that one and a very acute effect on hormone-sensitive lipase. There's one more thing that is, and this is just, look at the same thing. Here's the ATGL, adipose triglyceride lipase gene expression, and this is insulin down here. Those are all the amino acids in insulin. There's one more thing that has to happen, which PKA is going to do. This is going to phosphorylate pyruvate, and pyruvate is a coat around the lipid droplet. And so once PKA is active, it's going to phosphorylate things to permit lipolysis. This is a regulatory step too. A few years ago on campus, there was some guy, I think he was dressed as Spider-Man, and he went around and he was exposing himself to people. So that's what this is. He's pyruvate. This jacket right here is pyruvate. But inside of that jacket is a bunch of, triglycerides. And for the hormone-sensitive lipase, for the enzymatic breakdown, for the lipolysis, for the enzymatic lipolytic activity, these enzymes have to have access to it. And so you have to open that coat, right? You have to phosphorylate pyruvate to do it. So just another look at all this same stuff. Insulin is going to mobilize GLUT4. It's also going to block lipolysis. PKA would be turning on hormone-sensitive lipase, would be phosphorylating pyruvate to get access to that lipid droplet, but it doesn't work because insulin is in the way. And this is just a look at the two things. You should know most of the stuff that's on here. PDE, there's a bunch of kinds of PDE. 3B, this is fat. So if you want fat metabolism, it's phosphodiesterase 3B. Adenylate cyclase, right? And a beta adrenergic receptor, that's insulin receptor substrate, there's PI3K, phosphoinositide dependent kinase. We'll talk about that one later. Protein kinase B, you convert PI3K, converts PIP2 to PIP3. PIP3 allows that to phosphorylate activate PKB. PKB is going to turn on PDE. There's evidence that PI3K is going to turn on PDE. PDE is going to convert cyclic AMP to regular AMP, abolishing this signal. So PKA doesn't get turned on. PKA turns on hormone-sensitive lipase and pyruvate. That's lipolysis. So adrenergic stimulation, insulin abolishes it. That's the acute effect of insulin, and the expression of adipose triglyceride lipase is a more chronic obstruction of fat metabolism coming from insulin. So the narrative version, insulin binds to its receptor, a cell surface receptor, insulin binds to that. Stuff happens, PI3K gets activated. And then other stuff happens, PKB gets activated. PKB activates phosphodiesterase. Phosphodiesterase converts cyclic AMP into AMP. PKA does not get activated because AMP doesn't activate it, only cyclic AMP does. So hormone-sensitive lipase and pyruvate do not get phosphorylated. Lipolysis is stopped. The next lecture, we'll start to get into, I hope we'll get into some like the tips and tricks and strategies for fat loss. We'll see how far we get. But the different kinds of fat, so white fat, brown fat, beige fat, we'll talk about those. The fate of those free fatty acids, right? You free them from their triglyceride. And where do they go? And what is their fate? And then this is what we'll end with, is stuff that can help claims that people make that this helps fat loss that aren't actually true. And then claims that are true, stuff you can do, nutrition, supplements, exercise, thermoregulation strategies, stuff like that to accelerate fat loss. Okay, that's it. Questions for today? Team 2 is catching up. Thanks to JP's Star Wars trivia. Everyone's still sitting. I feel like I still need to say stuff. All right, I'm gonna stop the recording.